we have the equation y equals cos x between minus pi over 2 and pi over 2. So I'm just going to sketch that out to begin with. It looks like this. That's pi over 2. That's minus pi over 2. And then we're told that a rectangle ABCD is drawn so that A and B lie on the x-axis and C and D lie on the curve with this equation. So here's one such rectangle. See, this should be symmetrical about the y-axis. And then the point A has coordinate P0, where 0, or P is between 0 and pi over 2. So this has got to be P, and that's going to be point A, in fact. This will then be minus P because of the symmetry. And this line here will therefore be cos P. So find an expression of this area of this rectangle. Well, the width is 2p and the height is cos p. So that's our area. This is where it gets interesting because we're interested in where we can maximize this area. So obviously if you put it down here, it's going to be really small. I mean, it's got a large width but a small height. If you put it up here, it would have a large height but small width. So it's going to be an optimal point where P is to maximize the area of this rectangle. And we can do that by, we can find it by differentiating this function because we have the area as a function of P. So I know I've used A as the point, but I'm going to refer to the area as A now. And we can differentiate with respect to P and use the product rule. So differentiate 2P to give 2. And then differentiate cos P. And this will equal 0 at the maximum, or when the area is equal to S. And P at this point is equal to alpha. So therefore 2 cos alpha will equal 2 alpha sine alpha. By just rearranging, I can cancel the 2's out. And then I just need to think about this equation here. So you could either write it as cot alpha equals alpha, but I'm going to go with tan alpha is equal to 1 over alpha. And I think it's worth we can't solve this exactly, by the way, because we have a trig function on the left and a reciprocal on the right. We can deal with trig functions when they're equal to like a nice number, but no, this has got alpha in it. But I'm gonna sketch these two curves. Y equals tan alpha, and by the way, we know. Let's just recap. We're trying to show that alpha is between pi over 4 and 1, and we know that P is between 0 and pi over 2, so I only need to draw tan alpha between 0 and pi over 2. Looks a bit like that. And then draw y equals 1 over alpha. So I know that it's between 0 and pi over 2, but we're trying to show that it's actually, we can narrow it down to pi over 4 and 1. And one way to do this is to use the sign change rule. So let f of alpha equals tan alpha minus 1 over alpha, if we can show that there's a sign change between when we put alpha equals pi over 4 in and alpha equals 1, then we know there's going to be a root to the equation between these two values. So first of all, pi over 4. Tan of pi over 4 is just 1. 1 over pi over 4 is 4 over pi. And pi is like about 3, so this will definitely be less than 0. We don't know the exact value, but it's going to be less than 0. Meanwhile, f of 1 is going to equal tan 1 minus 1. Now, remember, pi over 4, like tan of pi over 4 was 1, so I'm just going to write to the left that like that's smaller than 1, so tan 1 is going to be greater than tan pi over 4. So tan 1 is going to be greater than 1, and therefore this is greater than 0. So there is a sign change. And f alpha is continuous on the interval, not everywhere, but on the interval. Hence, and that is what we're asked to prove. Next up, we're asked to show that S is equal to this. Well, we have the area, remember, is equal to 2p cos p, and the max occurs when tan p is equal to 1 over p. We're using alpha before. So we can basically substitute in for, we can try and substitute in for cos. So if tan p is 1 over p, and here's p, tan is opposite over adjacent, so this is 1 and this is p. Using Pythagoras' theorem, this is going to be p squared plus 1 square rooted. So cos p is going to equal p over the square root of p squared plus 1. And hence, S will equal 2 alpha. I'm kind of using this interchangeably, aren't I? I should just write here p equals alpha. So hence S equals 2 alpha times alpha over, I'm going to write it as 1 plus alpha squared, because now we can bring it together. So we get 2 alpha squared over the square root of 1 plus alpha squared, as we needed. Now, in the final part, we are asked to show that S is between these two values. And that's going to mean we need to use the results from B and C. We know that alpha is between pi over 4 and 1. This is a really interesting question, by the way, because we can't actually work out what S is exactly. But, you know, through these methods of differentiation and so on, we can get this range of values. Really good. So recall that pi over 4 is less than alpha, which is less than 1. Therefore, 2